Okay, yeah, it's begun. So, what we are going to do today is it's a new topic. Okay, so we have been doing Q learning and you got introduced to a bit of concepts in learning. What we'll do today is what is this notion called base nets? Okay, it's a way in which you analyze what kind of features, and it's a kind of data analysis kind of approach. But before I get into base nets, what I want to do is I just want to give you some motivations for this topic, because if you just see it, it's probably you're not going to appreciate it. You don't know why we're doing some of these things. So I just want to give you a flavor of it. And I'll also do a bit of a probability review just to remind you of some of the things which you've learned in your probability class, and we'll be using some of those extensively. So I gave you a heads up last time to prepare a bit on to brush up some of the basics. So we'll just quickly do a recap, and I point out what are the things that you need to keep in mind as we go along. Okay, so yeah, so probability, we have been now using it a bit in Q learning, also in MDPs we have been seeing it, but more formally, what do you do like when you have an event, so an event E, and you want to estimate the probability of this event? What do you do? It's if you have some data to estimate this, how do you do this? You did something like this in model based learning also, right? What was this thing? If you had some data and then you wanted to estimate this probability.
The number of times the event occurred by total number of samples or
Yeah, exactly, right? So number of times the event occurred divided by the total number of samples. So that was the sense of probability. Okay, so that's what it's meant to capture. So it's like a frequentist estimate. This is called a frequentist estimate. Okay, so one thing I want to now just get into is this conditional probabilities, right? So this is something that you saw. You've seen this on and off. Even in MDPs, we saw this. But just to take an example, so let's just take maybe a simple example, like probably you have an event E1. So I'm going to do like this, standard example where you have three coin tosses. Okay, and so what I'm going to say is E1 is the event that you have at least two heads, and E2 is the event that you have the first toss gave a head. Okay. So this is just to remind you of things and how you would compute this. So what are the possible things in your sample space? Can you tell me? So you have coin one, coin two, and coin three. So what are the possibilities here? So this is the outcome. So C1 is the outcome of the first toss, C2 is the outcome of the second toss, C3 is the outcome of the third toss. So what all can you
there
get
will be
here?
8 possible combinations.
H
All hits, all
Yes,
tails.
H
yes. So let's take all heads. Then what do you get
so
here? So see.
E1 and E2 given, so we will just directly write whatever possible.
Okay, so let's just write this configuration first, C1, C2, C3. So let's just go step by step. So what are the possibilities here?
Head, tail,
Tails,
So head, head, tail. Somebody said head, head, tails. Then
head, tail, head,
head, tail, head. Yes.
tail, head,
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 tail, tail,
Head, tail, tail. Correct. Then
tail, head,
tail,
head,
head, head,
tail, head, head. And now
tail,
what
head,
is it? T, T, H, T. Yes. Next this
tail, tail, head,
tail, tail, head. And
all tails.
finally all tails. Okay. So these are the 8 possible, outcomes that you can have. And so let's just write E1 and E2. I'll just put a tick wherever each of these applies. Okay. So where all does E1 apply? So that's at least two heads, right? So you will have something here. This qualifies. This qualifies. Then you have this qualifies, and anything else? This one, right? Yeah. So this is where you have at least two heads, and E2 is the first toss gave a head. So that's basically all of this, right? So now if you want to find, the probability that, let's say E2 given E1, right? So let's say probability of E2 given E1. So what's the probability that, the first toss gave a head, given that at least you
And there
got
should
two
be
heads,
in
right? So what is
E1,
this value from
the
here?
fourth one. So
Uh, can you
E2
say that
and
again?
tick for E2. Uh,
For this one, right? First toss gave a head. Yes, yes, yes. Okay, cool. So that's true. Right. So now, yeah, can you tell me what's this probability E2 given E1? How do you compute this?
Ma'am, 3/4.
3/4.
3/4. So how did you
Ma'am,
get
total
this?
number of cases of E2 were four. Like there were four possibilities of E2, and only in three E1 was also satisfying. That's why it's 3/4.
Okay, so total number of, so what did you say the first thing? The total possibilities for E2 was 4, and then out of them only 3. Is that what you said?
Yes, ma'am, because E1 is satisfied for three cases only. That's why it's 3/4.
Okay, so what you actually are saying is you did something like this, right? E2 intersection E1, and from what you say, it sounds like you did this. Out of the total number of possibilities that you had
Ma'am, I
E2,
think in the
so
below
that
P
was
of
these
E1,
four.
not E2.
Yeah, yeah. So, I mean, I'm just trying to clarify that. So, who said, I don't know who said this, that, you take the four possibilities of E2. Who pointed that out?
Ma'am, Prakhar, like
Yeah,
the
Prakhar.
yes, ma'am.
Okay, okay. Yeah. So, Prakhar, so there's a slight difference. So, what you do is out of the things that your new universe has to be this E1, right? So you look at this universe, and out of this, you see the number of times in which, I mean, so your universe is just, okay, so let me just mark this in red. So this one, uh, this, and this. Okay, so the ones which are marked in red. So you look at those four events, and out of that, you see the ones where E2 occurred. Okay, not the other way. Okay, so what you said was this, it boils down to this. Okay, like that you take all the possibilities where E2 happens. So basically these four ticks, and out of that you take the three. So that's not how you do it. It's the other way. Okay, so this is not right. So what you need to do is probability E2 intersection E1 by probability of E1. Okay, so your new space is E1, wherever E1 happens, and then you filter out wherever E2 occurred. Okay, so that's how you would compute this. Okay, another way to do this is, yeah, I mean, you explicitly compute the intersection probability. So the intersection happens in these three cases. So that is 3/8 if you assume that all tosses are independent. So 3/8 divided by probability of E1. So that is these four cases. So 4/8. Okay, so that also gives you the same answer. So 3/4. Okay, so these are two ways to compute the probability. So you've got to be careful about this, what you condition it on. So things will change if you, I mean, for this example, it doesn't change, but you can have examples where probability of E2 given E1 is different from probability of E1 given E2. Okay. Right. So that's about conditional probability. Now, more generally, if you have like a collection of events, let's say E1, let's say you have this event like this, E3 given E1, E2. So the general recipe to compute this is you just take the intersection. So So E3, E1, and E2. So when I write something like this with commas, it means it's an intersection. So this is same as probability of E3 intersection E1 intersection E2. Okay, it's the same thing. I'm just writing it in this way. So this is just probability E3, E1, E2 by what?
P of E1 conjunction E2 intersection E2.
E1 intersection E2. So let me just write it like this: E1, E2. Okay, and so again, so what you can do is, it's just a change of just rearranging the terms. What you can get is this joint probability. So E3, E1, E2, it's just the same as E1, E2, E3. So it's ultimately you're talking of the same event. So this is just probability of E1, E2 times probability E3 given E1, E2, right? And another thing is you can just write this probability E1, E2 as probability E1 times probability E2 given E1, and so on, right? So this is actually what is called the chain rule of probability, right? So this is chain rule. So have you seen the chain rule in your probability class? Did you see this?
Yes, ma'am.
Yes, right. So more generally, if you have like a collection of events, E1 to En, what you do is you take the first event, then you take E2 given E1, then probability E3 given E1, E2, and so on. Okay, so each time you take probability EI given E1 to EI minus 1, and so on. You keep doing it till you get all the N events. Okay, so now coming back to this example, like, if you were going to estimate these probabilities from data, so typically, in these kind of coin tosses kind of thing is, you have these individual probabilities beforehand, these intersection probabilities, all this is there. But suppose, this was something that you had to estimate from your data. Okay, so then what you would need is you would probably need to estimate all of these quantities from your data. Okay, and so there are a lot of these kind of terms which come in the chain rule. Okay, and so you will need a lot of data to get these kind of terms. Okay, so sometimes, if you can simplify these kind of expressions, it helps. Okay, so that's what you will see in base nets. Sometimes, this is the most general way to write this kind of a joint probability. But sometimes, if you have to condition on so many variables, going further down in these product terms, you have to condition on so many terms, and that sometimes becomes a bit hard to estimate these numbers. So if you can simplify this further, it helps. Okay, so we will come to this in a bit. So now another thing I wanted to also talk to you about was, this total probability. So this law of total probability. Right. So let's just do one example. Right. So suppose there was this smuggler, right, who you're trying to capture, and the smuggler is trying to escape. Okay, so there's a smuggler who is trying to travel out of the country, and so there are three possible cities through which he exits. Okay, so let's say there is an airport uh, P. There's an airport, or maybe let me just call it A, B, and C. So airport A, airport B, and airport C. Okay, and let's say that these airports have like different levels of checks. So probability that if you that the smuggler will get caught if he was at airport A, if he took airport A, maybe it was something like zero point 0.1, very lapse security. Probability that he got caught if he took airport B, if he took that route, maybe it was something like a zero point 0.7, and probability that he got caught if he took the route via airport C. So let's say it was something like zero point 0.4. Okay, so and so the smuggler has these three possibilities, and probability that he chooses A. Let's say like all these are with probability 1/3. He chooses all of them. Okay, choose B is 1/3, and probability that he chooses C is 1/3. Okay, So he doesn't have any particular preference. Now, yeah, so let's try to estimate what's the probability that, he took, say, airport B, given that he didn't get caught. So he didn't get caught. So what is the chance that he took airport B? Didn't get caught. Okay. So how would you compute this? So probability that he took airport B provided given that he didn't get caught. So how with these numbers, how will you compute?
P of B into P of not caught given B, and
So
then
P
the
of
denominator
so P of not caught given B times what did you say? P of B.
P of B, yeah. And in the denominator, we take a sum of all these type of terms
So
for A,
these
B,
type
and
of terms for A, B, and C. So given everything else, right? Probability of not caught given given A times P of A plus all this, right? So that's what you mean. And you take not caught given B times this, right? So, yeah, so what did you apply here when you wrote this formula? There's a particular name, right, for this way of writing things?
Well, base, base, yeah.
Base rule,
Base rule,
yes.
right? So you did base rule. Somebody said something else also. Or was it just base rule? I thought I heard something else also being mentioned. Okay, so what happened was probability of not caught given B times probability of B. So effectively, this was actually probability of not getting caught, right? So that was what came in the denominator, and that evaluated to this sum. So this denominator you got from the total law of probability, right? And yeah, so it's a combination of this, whatever this entire step is a combination of base rule and the total law of probability, and that's how you get this. So you see that there are these various set of conditioning, various set of conditional probabilities that people are interested in. Now, why did we decide to fix these as the numbers, right? Why didn't we, I gave you these numbers and then we computed that what was the probability that he took B given he didn't get caught. But why didn't we start off with the other way? So probability of, taking B given he didn't get caught. Why didn't I give you such a model? Right. So the reason is that these numbers are what you think of naturally, right? These are the numbers that you when you think of the problem, you have a way to put these numbers down, and that's why the base rule is useful. I mean, it's not just a very algebraic thing. It's because typically this probability that we write in the numerator, that you have an easy way to quantify that, but the other one on the right hand side, you don't have a way to compute that. But finally you want to see that you see this outcome that he didn't get caught, and then you want to see okay, so what's the probability he escaped from airport B, and then you do some operations there with airport B. Okay, so that's the intuition for base rule. So it's not just an algebraic exercise. So that's what I just want you to understand. Okay. All right. So we did the chain rule. We did the base rule, total law of probability, and what else did we do? We did conditional probability. Okay. So now let's just talk about independence a little bit. So when do you say two events are independent? So let's say E1 and E2. So when do I say that they're independent? What is the what's the notion of independence? What does it mean?
There is no effect of let's say if we have probability of event one, if event two happens, and it equals to probability of event. Means there is no impact of E2 on E1, like whether E2 happens or not, E1 is independent of E2.
Yeah, so it's yeah, exactly. So each don't impact the other, right? So let's just look at this example. So maybe, so let's say, you go to a school, you go to maybe it's a high school or, a school with all classes. And let us say that, you look at, there are all these children there and you measure the shoe size, okay, the shoe size of children. So this is one event, or it's not an event. So let's say it's a random variable, right? So this is one random variable, and then I have like let's say the mathematical reasoning abilities of these children. So you keep a math test and their score. Okay, so that is the second random variable. Okay, so are these two independent or are they dependent? What do you think? How many of you think it's independent?
They are independent.
They're independent?
Yes.
Okay. So maybe let me just ask people to type. How many of you think it's independent? Can you just type whether it's independent or not independent? Not independent. Sahil said not. Okay. What about the others? Independent. Can be independent if all the children are of the same age. All right. Independent. Mm-hmm. Any other answers? Himanshu? Okay, Himanshu doesn't have any thoughts. Karthik?
Ma'am, can you once again show the means even and E2 status?
Yeah. So these are the random variables. I wouldn't say it's events, but these are the random variables. So you have the notion of independence of random variables also, right? So, yeah. So are they independent? That's the question. Tanuja said it's independent.
Then it might be the case like if the samples are taken from the same class, then they're independent. But if we take randomly from the entire school, then they might be dependent.
They might be independent. Okay, so fine. So Tanuja says if they're from the same class, they can be dependent. If otherwise they're independent. Okay, fine. Any other answers? Vivek said independent. Okay. I just want to hear all of your thoughts also before get into a discussion of what actually the answer is. Right, Rishabh?
Yes, ma'am.
Yeah. So what do you think?
Ma'am, I don't means I have conflict in my mind means I can't say anything.
What is a conflict? Let
Means
us
I do not
discuss it.
understood the meaning of mathematical induction here. Means why you are considering the comparing the two events, one in mathematical induction, mathematical reasoning, and so yeah.
No, so this is just something that I just want to think. Is there any correlation between these? Right? I mean, why I want to do that, like forget that. I want to do many crazy things in life. So let's say this is one such crazy thing I want to do. Okay, but if you look at this, what do you think? Are they independent, or do you think there is any correlation between them, or do you think they're not correlated? I mean, of course, correlation and independence are two different things. They're not exactly the same. But let's say independence. So do you think one impacts the other? So if the shoe size is small, does it mean that the mathematical reasoning is small or large? Is there something you can say, or it's it's no connection between the two? What does it mean?
Ma'am,
Rishabh, what's the conflict? Yes, tell me.
ma'am, I think if the shoe size Ma'am, I can't give any answer regarding this.
Okay. No, but tell what's the confusion? What's causing the conflict? Let's discuss that. That's also a useful thing, no? That what are the possible ways you're thinking? Let's see that.
Ma'am, I think it's independent only, means not dependent.
Non-dependent. Okay. Yeah, it seems like very bizarre things, right? Shoe size and mathematical reasoning. So why would there be any connection between the two, right, Rishabh? That's what
Yes, ma'am.
thought process, right? Yeah, fair enough. So that's what you know at a first glance, that's what it seems like. Okay. So Karthik Anand said independent, Sanjay said independent, Vivek Kaushik is becoming philosophical, don't judge a book by its cover. Okay. It would become dependent if sample size increases. Okay. So there's a mixed set of opinions here. So let's just get down to it. So yeah, it's true. When you just look at it, it seems independent. But what happens is there are some other factors here. There are some hidden factors, like somebody pointed out, which class are they in? So the class they are in, if you have this information, so which standard, like fourth standard, fifth standard, which class are they in? If that is known, this impacts two things, right? I mean, this if you're in a smaller class, if you're in primary, then maybe your shoe size is very small. Okay, so that impacts your shoe size. Okay, and also your mathematical reasoning also depends on which class you are in, because the things that you know already and the techniques that you know. Okay, so if you know the class, so let's just write it like this as a variable. I mean, so this is also a random variable, like which class they are in, and there's a shoe size, and there's a mathematical reasoning ability. So if you know the class in which they are, then what would it be if it's a fixed class, right? Actually, if you know the class, these two are like independent samples, right, of the same thing. Like you pick a guy, and if you see different set of people, then you will see that they're independent. Okay, so yeah, if you know the class, then there's some correlation. But if you don't have any information about the class, then there's nothing you can say. So this is there is this conflict that has been there, and it requires some kind of thought process to analyze this. Okay, so these are the things, right? So if you know the class, so probability of shoe size, is it independent of the reasoning given the class, right? So this is what is the notion of conditional independence. If you have the class, these two are, probably they are, I don't know, are they dependent or they're independent? If you have the class information, so everybody in fourth standard, then if you see the shoe size and math reasoning, are they dependent?
Independent.
They're independent, right? So if you have the class, they are independent. But if you don't have the class, then maybe there is some correlation. A small shoe size means that they are from a smaller class. So that in turn means that the reasoning abilities is not much. So you can draw that kind of inferences. Okay, so that's what I wanted to draw from this example is that some things are not just independent if you look at it, though they seem like very bizarre two things, but there are a lot of latent things in the environment which actually induce some dependence between them. So here what it means is that probably, I mean, shoe size and mathematical reasoning, these are dependent, but if you know the class, they are independent. Okay, so that's what this would turn out to. So more generally in complex systems, there are this entire set of variables, and you want to analyze this. Okay, so the notion of dependence and independence, and some part of your network is, or some part of your environment is visible, like for example the classes of the students. Okay, so in a different network, I mean, in a different problem, some things are observed, some things you don't observe, and then you're interested in seeing, what are the dependence or independence relationships. Okay, so I just wanted to draw on this aspect of conditional independence here. Okay, um, So what is conditional independence more formally? What it means is that, suppose you have probability of let's take three events. So E3 is conditionally independent of E2. So there's no probability here. Sorry, just writing something. So E3 is conditionally independent of E2 given E1. What it means is if you compute the probability of E3 given E1 and E2, what's going to happen is, the presence of E2. I mean, E2 is not going to affect it. So this is just going to be probability of E3 given E1. So given E1, E2 doesn't matter into the picture. So this is what is conditional independence. Okay. Why are these kind of dependence relationships also important? We'll see one example. So you've all learned about the naive Bayes classifier, right? Have you learned it in your probability class? Yes, no? Okay, the class is quiet. What's going on?
Don't remember it.
Okay, You don't remember? Okay, fine, no worries. So we will recap it. So let's take, maybe a relevant problem. So just give me a second. I'll just switch on the fan. It's just become very hot. Just give a second. Yeah, I kind of forgot that I'm in Goa and it's hot. So, okay. So, yeah. So, there's a question here. Vivek is asking. We can also assume that we're given gene code and many things. The answer will become discrete or definite. So, Vivek, I don't know if I understand your question fully. Can you just clarify what you mean?
Ma'am, if we assume like we toss a coin and we know wind direction in many factors, then we can say that the coin will land on head or tail. So, but ma'am, in probability, if we are given something, we assume it independent of other natures.
Yeah, so what you're saying is there are a lot of other factors in the environment which play a role, right? And so you cannot just say things whether something is independent or not, right? Whether two random variables or two events, whether they're independent or not, right? Vivek, that's your point?
Yes, ma'am.
Yeah, exactly. So that's the point that I was trying to convey through this example. Things are not very obvious at a first glance. Okay, and that's why there is a reason to do these kind of analysis. So let's just get into I just want to motivate it from the perspective of a classifier. So all of you know what a classifier is. I mean, you haven't learned it in a course, but I think now people are reading up about machine learning and everything everywhere. So what is a classifier? Um, it's basically a categorization task, right? You have some instances, like you have some x1 to maybe some xt, and the idea is to categorize them. So either for each of them you give a value +1 or -1, maybe. Okay, or maybe 1 to D, something like that. Not D, but K classes or something like that, right? So for each data point that you have, you try to categorize it into different types. So let's take an example. So what I'm trying to do is, as faculty, many times we are interested in seeing like which of this, I mean, how many students, or whether a student is going to do higher studies or not. Okay, so let's just take this example. So there are all these students, like maybe all of you, and so what we have, like, let's to keep the problem simple, let's just take we just look at three features. So one is like you have your 10th marks and 12th marks, okay, and maybe your undergrad, like your final CPI or something like that. Okay, or maybe like your semester wise CPI, that's also something maybe we have. Okay, so but let's just keep it simple at these three quantities, and you want to see whether are they going to do higher studies or not. So higher studies or not. Okay, so this is what you want to understand: higher studies or not. Okay, so I'll say that, I will denote this by a variable. So I will say that y is equal to +1 for higher studies. And I will say y is -1 if, the person doesn't take up higher studies. Okay, and so you can think of these things, right? These are like what are called the features. Okay, and the 10th or 12th marks and your CPA. So it just gives an indication of the interest of the student. Of course, there are many other factors, but just let's keep it simple right at the moment. And what I want to see is, whether they go for higher studies, and maybe I have some access to some past data. Okay, and what I want to do is, I'm going to get a new student. So there's going to be an X test. So this is like x1, x2, x3. So these are the features. So x is x1, x2, x3. Okay. And I'm going to see a new test instance, which is x test. And I'm going to, so this is going to be a vector again. So x test 1, so feature 1, which is the 10th marks. Then I have x test 2, which is the 12th marks, and x test 3, which is the CPI of the student. So what I will have to tell is what is going to be the value of y test, right? Given x test. So given these are the features. Okay. So it's as if y is, the way we are modeling it is y is a random variable because we don't know. I mean, it's not like, if all these are high, then yeah, if all these are high, maybe y is +1. But if, one is high, so if 10th mark is low, but 12th and CPI is high, then is y going to be +1 or -1? You can have it either way. Okay, so that's why it's a random variable. And typically, this is what you want to learn. Okay, you want to see the value of y test. So what this means is probability that y test is 1 given the values of x test. So given x1 is this, x2 is this, x3 is this. Okay, so this is what you will want to evaluate. Okay, and how would you do this? Just looking at this probability, it's a conditional probability. So based on what you have learned, anything you can apply from what we discussed so far?
Base zero.
Base rule, right? So how would that work? So that would be, can you tell me the expressions?
P of x test given y equal to 1
Y equal to
into
1.
probability of y equal to 1
Yeah.
upon the same term and then take y equal to 0 for the next.
Yeah, so you can use the total probability, right? Yeah, so this is what you would do if you were to apply Bayes rule. So remember this one, probability x test given y equal to 1. So this was like, so I will represent these, okay, so these are the random variables, x1, x2, x3. So probability that, let me call the random variable itself as x1, capital X1, x2, and x3. So x1 equal to x1 test, x2 equal to x1 test, x2 test, and x3 equal to x3 test given y equal to 1. So this is the random variable. Like y is the random variable corresponding to whether it's going to take higher studies or not, times probability y equal to 1 divided by this whole thing, right? I mean, you have a summation over different possible values of y. So either for y equals 0, you can again compute these numbers, and for y equals 1, again, you can compute. Okay, so I'm just not writing the denominator. So yeah, so this is what you would do, and what if I have to write it, one step before, it would be like it's the joint actually, right? So this numerator is just probability of x test, comma y, given, divided by this whole thing, right? So this is on the numerator, what you actually have is a joint probability. Now the thing is, remember from the chain rule, what you should have ideally done was, condition on everything else. Okay, so there are different ways to condition it, but why was it that we chose this particular way of conditioning it? Okay, and in neighbors classifier, what you further do is, you take this numerator and you say that, all these factors, these x1, x2, and x3, they are independent given y. Okay, so further what you will do is you will just write probability x1 equal to x1 test given y equal to 1 times probability x2 equals x2 test given y equal to 1, and times probability x3 equal to x3 test given given y equal to 1. Okay, and of course you have times probability y equal to 1, and so on. So the point is, this term here, you're going to do a simplification. That's what the assumption in naive Bayes is, that all these are independent given y, and each of this you are able to learn with some data. Okay, so you observe some data of all the x's and the y's, and this factor you compute it by, you look at all the possible values of x1 and when y equal to 1, and then you estimate this, right? Each of this you do it that way. Okay, so here there was this assumption of conditional independence. So when we wrote this formula, I didn't actually tell you this. So what this meant is probability of E3, E2 given E1, right? So this is also another way to write this is probability of E3 given E1 times probability of E2 given E1. So that's another way. So these are two different ways to write conditional independence. They boil down to the same thing essentially. Okay, so that's what naive Bayes uses. But actually, why is it that we went for this kind of a representation and not for any other thing? So this joint probability, actually there are very many ways, right, to write this. So you could actually write this as probability y equal to 1 times probability x1 given y equal to 1. I'm just writing this as x1 for shorthand. Okay, so what this means is x1 equal to x1 test given this. Then you could write x2 given x1 and y. Then probability of x3 given x1, x2, y. Right? This is also another possibility, right? To write this joint probability. So why is it that we didn't do that and we went for something like this? Okay, so that requires some more analysis, and that's actually these kind of questions are the foundation of what we'll call as base nets. uh, how do you evaluate these kind of joint probabilities? So actually this whole thing, actually the numerator, how do you evaluate these kind of joint probabilities in very complex networks? Okay, so that's actually the focus. Typically, you represent each of these random variables, as a graph. So we will see that in the next time. And usually it's a complex network, and you're interested in these kind of joint probabilities. Okay, so how if you have a simpler model, it's better and better. So this kind of conditional independence actually simplifies a lot of things in terms of even the estimation, the amount of data that you need. Okay, rather than if you go for this kind of vanilla application of this chain rule, you have like so many parameters, and each of these parameters requires at least 10 times the amount of data. For each parameter you need at least 10 data points. Okay, so then it becomes hard to estimate. So that's why we do some simplifications, and in fact a lot of things in machine learning is about designing simple models, because you want to enhance learnability, but of course at the same time you want to keep expressibility, like you want the model to be powerful, but at the same time you want a simple model. So base nets is a way in which it helps for these kind of things. Okay, so maybe I'll just stop here, and maybe if there are any questions I can hand back. Yeah.
Ma'am, I have one doubt. Means, as you initially mentioned that in the conditional probability means conditional case as you use in the base case means name based classifier. You mentioned that we consider the every feature as an independent.
Which one? These
Ma'am,
ones?
here, yes, ma'am. As you
Yes.
calculated the P of the x1 is equal to x1 test and x2 is equal to x2 test.
Yes.
Ma'am, here
This
you
one.
consider, yeah, ma'am. Here you consider that they are conditionally independent or solving the things.
Yes.
So
Yes.
it
Yes.
is only applicable in this case only. Means in the naive Bayes classifier only we consider this thing. Means we cannot generalize this thing for the others.
Yeah, yeah. So what I'm saying is in naive Bayes classifier, this is an assumption made about conditional independence. Like given the class label, so this Y is called the class label. So given this class label, the features are generated independently. That's an assumption that naive Bayes makes. Okay, but more generally, yeah. So more generally, that is something that it needs some justification. Why is it true?
Ma'am, in the neighbors, means what I think that because they have too much features, so that's why they consider it as an independent. Because unless it will create too much complexity, so that's why we consider it as an conditionally independent. But
Yeah.
in normal case, we should not consider it as means conditional independent, I think.
Conditional dependent. Yeah, so exactly what you say is reflected in this. So ideally, if you didn't look at conditional independence, you would either have to, model this probability given y equal to 1. Like given y equal to 1, the probability of generating all these features, you have to assume some kind of dependence among features, and that maybe it's not, very, computationally feasible. So that's one thing. And other possibility, if you didn't do that, maybe then to estimate this whole numerator, or this is just probability of x test and comma y, right? This numerator is just this. Another thing, possibility is to have a model like for this joint probability. So that would mean like, writing out this chain rule, right? In complete generality, if you want to do it, you have to write this. So again, it's the same issue that, there are a lot of parameters here. Okay. And to estimate all of them with data, it's not possible. So conditional independence is a simplifying assumption, right? So it makes
Okay.
things a little bit easier,
Then it will
right?
applicable for the all the case, or it will applicable only up to this case.
Yeah, so naive bias so this is a naive bias classifier. So let me just make it very explicit. So for naive bias classifier, we use conditional independence. More generally, we cannot say. Okay. So what I'm trying to get at is how do you generalize this idea that is being used in naive bias classifier? So here we say that conditional independence has this form where x1, x2, x3 are independent given y. Okay, but if you have another kind of a problem, if you have a very big network with a lot of variables, then what is the underlying how can you simplify the model further? Okay, so I'm just trying to generalize this idea a little more, right? So in more like if for naive Bayes classifier, this is a feature, the conditional independence. But if you take some other classifier, maybe they don't make this assumption, right? So what is the right thing to be doing? How should you be analyzing the data? How should you be analyzing these dependencies? So that's the question that I want to just put across.
Okay.
Rishabh, it's clear. Let me.
Yes, ma'am.
Okay, so yeah, we will continue this from tomorrow. So I will lead on. I mean, I will from this point, I will go to the base network and start from there. Okay, so thanks everyone. If there are no questions, yeah, you can leave, but I'll be here for some time anyway, if you want to ask.